Fundamental theorem of arithmetic. Class 10, exercise 1.2. Fundamental theorem of arithmetic. Every composite number can be expressed as product of primes, and this factorization is unique apart from the order in which the prime factor occurs. Here we came across with some known terms such as factors, orders, prime, composite numbers, factorization, unique. Let us go through these words. First of all, let us try to feel the word factors and multiples. First of all, factors. It means that in how many categories the number can be divided. Divided means successive subtraction equally. For example, 6 can be categorized in 4 ways. Group of 1, 6 times. Group of 2, 3 times. Group of 3, 2 times. Group of 6, 1 times. So, 1, 2, 3 and 6 are the factors of 6. By using Euclid's division lemma, A is equal to BQ plus R. So 6 is equal to 1 into 6 plus 0, 6 is equal to 2 into 3 plus 0, 6 is equal to 3 into 2 plus 0, 6 is equal to 6 into 1 plus 0. By Euclid's also, it is very much clear that 1, 2, 3 and 6 are the factors of 6. But 4 and 5 are not the factors of 6. Here you can see by Euclid's division lemma, 6 is equal to 4 into 1 plus 2, 6 is equal to 5 into 1 plus 1. Here we are with remainders 1 and 2. So 4 and 5 are not the factors of 6, because 6 cannot be divided into 4 or 5 equal parts. This process of grouping a number into different groups as 6 of 1, 3 of 2, 2 of 3 and 1 of 6 is termed as factorization. Now multiple. It means that in how many categories the number can be multiplied. Means successively added equally. For example, 6 can be categorized in 4 ways. Similarly as in factors, here we also get 4 types. So 6 is a multiple of 1, 2, 3 and 6. Here 6 is not a multiple of 4 and 5 because after grouping in 4 and 5, it comes with remainder which can't be further grouped. Prime numbers. They are the whole numbers greater than 1, which cannot be expressed as product of 2 smaller whole numbers. Or it can't be divided in equal parts less than it. Or which have only 2 factors, 1 and itself. Or it can be grouped only in 2 ways. In group of 1 or as a whole group. So, the very first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29 and so on. Prime numbers. Let's have a look on some properties of prime numbers. Number 1. The smallest even prime is 2. Prime numbers greater than 5 will end with digit 1, 3, 7 or 9. Third one, every even number greater than 2 can be expressed as sum of 2 primes. For example, 4 can be expressed as 2 plus 2, 6 can be expressed as 3 plus 3, 8 can be expressed as 3 plus 5, 10 as 3 plus 7 and 5 plus 5, 20 as 3 plus 17 and 30 plus 7, 100 as 97 plus 3 and 53 plus 47 and so on. Now, to check whether a number is a prime or not, we have to check this with a trial method. If a number is divisible by a number between 2 and the square root of the number, then the number is not prime. For example, let us check 127 as a prime or not. Natural number near to square root of 127 is 11. So, between 2 and 11, there are no natural number which divides 127. So, 127 is a prime number. Let us check 177 as a prime. The natural number near to the square root of 177 is 13. Here, if 177 is divisible by a number between 2 and 13, then the number is not prime now. as number 177 is divisible by 3, so it is not a prime number. Let's have some more terms related to prime numbers. First one is twin prime. Pair of prime numbers having a difference of 2. For example, 11 and 13, 17 and 19, 41 and 43, and so on. So a question comes in a mind that, is there any formula for finding a twin prime numbers? Yes, we have. The formula is 6n minus 1 and 6n plus 1. For natural numbers greater than 1 and must have unit digit 0, 2, 3, 5, 7, 8. For example, let n is equal to 2. So the pairs of twin prime number are 11 and 13. For n equal to 3, the pair is 17 and 19, and so on. Now the co-prime numbers. Two integers a and b are said to be relatively prime, mutually prime, or co-prime if the only positive integer that divides both of them is only 1. Or in other words, we can say that if SCF of a and b is 1, then the numbers are co-prime. For example, 4 and 9. Here, neither 4 nor 9 is prime, but the pair 4 and 9 is co-prime. 10 and 49 is a pair of co-prime, and so on. 5 and 7 can be regarded as both co-prime as well as twin prime. Perfect number. A positive integer which is the sum of its proper divisor, excluding the number itself. For example, the smallest perfect number is 6, as 6 is equal to 1 plus 2 plus 3. Here, 1, 2, 3 are the proper factors of 6. 10 is not equal to 1 plus 2 plus 5, as 1, 2 and 5 are proper factor of 10. For 12, 1, 2, 3, 4, 6 are the proper factor of 12, but on adding 1, 2, 3 and 4 we don't get 12. Similarly, the second perfect number is 28, as 28 is equal to 1 plus 2 plus 4 plus 7 plus 14. Now here again a question arises in our mind that, is there any formula for finding the perfect number? Of course, we have. The formula is 2 to the power m multiplied by 2 to the power m plus 1 minus 1. For if m is equal to 1, first perfect number is 2 to the power 1 multiplied by 2 to the power 2 minus of 1, that is 6. Second perfect number is 2 to the power 2 multiplied by 2 to the power 3 minus 1, which is 28. And similarly, we can find infinite perfect numbers by using this formula. Composite numbers. The number which have more than 2 factors, or the number which are not prime other than 1. For example, 4, it has 2 factor 2 and 2. 6, it has 2 factor 2 and 3. 8, it has 3 factors 2, 2, 2, 2, 2. So the smallest composite number is 4. Or in other words, we can say that the number which can be expressed as product of primes, that numbers are known as composite number. Let us see the Euclid's fundamental theorem on composite number. Now, let us see fundamental theorem again. Every composite number can be expressed or factorized as a product of primes, and its factorization is unique apart from the order in which the prime factor occurs. 12 can be written as 2 to the power 2 into 3, or 12 can be written as 2 into 3 into 2, or 12 can be written as 3 into 2 into 2, which can be written as 3 into 2 to the power 2. It means order may be any order, but by commutative law, all are unique, that is 12. Here I have given some interesting abbreviation which are commonly used in mathematics, that is, and for example, Now let us have some interesting question. What will be the digit at unit place of 2, 3, 4, 5 to the power 2, 3, 4, 5, 6, 7, 8, 9 to the power 2, 0, 9, 8, 1, 2, 3, 4 to the power 1, 2, 3, 4, 3, 4, 5, 6 to the power 2, 3, 7, 8, 4, 5, 7, 8 to the power 4, 3, 5, 7, 6, 7, 8, 0 to the power 2, 3, 1, 7. What is happening here? So huge numbers. Can you predict the unit place of the number? Let us see what is the logic behind this. You will be very surprised to know that fundamental theorem of arithmetic is behind this, as every composite number can be expressed as product of its prime, so all these are also natural numbers. They can also be expressed as product of primes. Now let us see the basic logic behind this type of number. The number ending with 1 will have 1 at unit place of different power. For example, 11 to the power 1 will be 11, 11 to the power 2, again 121, 11 to the power 3, 1331, and so on. It means that the number ending with 1 will have 1 at its unit place. I think it is clear. Now let us see what happened when the digit end with number 2. The number ending with the digit 2 will end with a particular number as the power of 2 other than 0. Let us see what happened. 2 to the power 1 is 2, 2 to the power 5 is 32, 2 to the power 9 is 512, will end with digit 2 now. 2 to the power 2 is 4, 2 to the power 6 is 64, 2 to the power 10 is 1024. All the digits are ending with the digit 4. 2 to the power 3 ends with 8, 2 to the power 7 ends with 8, 2 to the power 11 ends with 8. So all these type of digits ends with 8. 2 to the power 4 ends with 16, 2 to the power 8 ends with 6, 2 to the power 12 ends with 6. Again all these type of digits ends with 6. If the power of the number ending with 2 is in the form of 4n, it will end with 6, where n belongs to the family of whole number. If the number is in the form of 4n plus 1, it will end with the digit 2. If the power is in the form of 4n plus 2, it will end with 4. If the power is in the form of 4n plus 3, it will end with 8. Let us see some examples. 5, 6, 1, 2 to the power 2, 3, 4, 5. Here, the power 2, 3, 4, 5 is in the form of 4m plus 1. Yeah, 4n plus 1. So, it will end with 2. For next question, 6, 7, 4, 2 to the power 8, 7, 5, 4. Here, 8, 7, 5, 4 is in the form of 4n plus 2. So, it will end with 4. Hence, we can find the digit at different powers of 2. Let us see what happened in the case of 3. The number ending with 3 will end with a particular number as power of 3. It should again be other than 0. 3 to the power 1 is 3, 3 to the power 5 is 243, 3 to the power 9 is 19683. All these ends with the digit 3. So in the next case, 3 to the power 2 is 9, 3 to the power 6 is 729, 3 to the power 10 is 59049. All these end with 9. Similarly, for 3 to the power 3, all digits end with 7, 3 to the power 4, digits end with 1. So see here, again we have a logic that if the power of a number ending with 3 is in the form of 4n, the digit will end with 1 and belong to the family of whole number. If the power is in the form of 4n plus 1, then it will end with the digit 3. If the power is in the form of 4n plus 2, it will end with the digit 9. If the power is in the form of 4n plus 3, the digit will end with digit 7. Let us take an example. 2473 to the power 7654, as 7654 is in the form of 4 into 1913 plus 2. So it will end with 9. Now let us see for the digit ending with 4. For the digit ending with 4, 4 to the power 1 4 is 4, 4 to the power 3 is 64, 4 to the power 5 is 1024. Again 4 to the power 2 is 16, 4 to the power 4 is 256, 4 to the power 6 is 4096. It means that if the power is odd, that is in the form of 2n plus 1, it will end with 4. And if the power is even, that is in the form of 2n, it will end with 6. So in the previous example, 1 2 3 4 to the power 1 2 3 4, the last digit will be 6 as the power is even, or in the form of 2n. Again, for the number ending with digit 5, will always end with 5, as 5 to the power 1 is 5, 5 to the power 2 is 25, 5 to the power 3 is 125. So in 2 3 4 5 to the power 2 3 4 5, the last digit is 5. For the number ending with digit 6, will also have 6 as the last digit for any power other than 0. Let us have a look. 6 to the power 1 is 6, 6 to the power 2 is 36, 6 to the power 3 is 216. So 3 4 5 6 to the power 2 3 7 8 will also end with 6. Very good. For the numbers ending with digit 7, it also has the digit at unit place, as there was in 2 and 3. Here the digit at unit place may be 7, 9, 3 or 1. This means that if the power is in the form of 4n, the last digit will be 1. If the power is in the form of 4n plus 1, it will end with 7. If the power is in the form of 4n plus 2, it will end with 9. And if the power is in the form of 4n plus 3, it will end with 3. So the question 987657 to the power 2348 is in the form of 4n, so it will end with 1. Similarly, for the number ending with digit 8, will end with 8426 for the power in the form 4n plus 1, 4n plus 2, 4n plus 3 and 4n respectively. So 4578 to the power 4357 is in the form of 4m plus 1. So it will end with digit 8. For the number ending with 9, if the power is odd, it will end with 9, and if the power is even, it will end with 1. So for 6789 to the power 2098, here 2098 is even, so it will end with 1. At last, the number ending with 0 will also end with 0. So 6780 to the power 2317 will also end with 0. Now, this property will help us to prove some NCERT problems, like prove that 6 to the power n will never end with the digit 0. Let us have the proof of it. Check whether 6 to the power n can end with the digit 0 for any natural number n. If the number 6 to the power n for any n were to end with the digit 0, then it could be divisible by 5. That is, the prime factorization of 6 to the power n would contain the prime 5. This is not possible because 6 to the power n is equal to 2 into 3 whole to the power n. So the primes in the factorization of 6 to the power n are 2 and 3. So the uniqueness of fundamental theorem of arithmetic guarantees that there is no other prime in the factorization of 6 to the power n. So there is no natural number n for which 6 to the power n ends with the digit 0. Explain why 7 multiplied by 11 multiplied by 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. In the first case, we can take 13 common and it can be written as 13 multiplied by, in bracket, 7 multiplied by 11 plus 1. As in above case, the product of two numbers, so it is composite. And in second case, we have taken 5 common as and shown the given number as a product of two numbers. So again, this is also composite. Let us express some composite number as product of primes. 140 as 2 to the power 2 into 5 to the power 1 into 7 to the power 1. Similarly, 156 as 2 to the power 2 into 3 into 13. And I have shown different numbers as product of primes. By fundamental theorem of arithmetic, every composite number can be expressed as product of primes. Let us find SCF and LCM by prime factorization method. First, 12, 15 and 21. Here the prime factorization of 12 is 2 to the power 2 into 3. 15 is 3 to the power 1 into 5. 21 is 3 to the power 1 into 7. So, SCF means highest common factor of 12, 15, 21 is the number which is common in all the 3 prime factors is 3. So, product of the smallest power of each common prime factor in the number is SCF, that is 3. For LCF, product of the greatest power of each prime factor involved in the number. For that, LCM of 12, 15, 21 is 3 into 5 into 7, which is 105. In second case, 17, 23, 29, all 3 are prime number, so SCF is 1 and LCM will be the product of all the 3 numbers, that is 1, 1, 3 and 9. For 8, 9, 25, again SCF is 1 and LCM is 1800. Find the LCM and SCF of following pairs of integers and verify that product of LCM and SCF is product of the two given numbers. Let us take very first example, 26 and 91. 26 is 2 into 13, whereas 91 is 7 to 13. So here, SCF is 13 and LCM is 2 multiplied by 7 multiplied by 13, that is 182. For LCM, we have a formula, SCF multiplied by some number. You can see here also in the example, SCF is 13 and LCM is 14 into 13. So, product of two number is equal to the SCF multiplied by LCM. In the next example, 510 and 92, SCF is 2 and LCM is 23460. Here also, product of LCM and SCF is 46920 and product of the number is 46920. Here it is verified that LCM multiplied by SCF is product of two given number. And second thing we notice that LCM is multiple of SCF. Let us have a situational problem. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they start at the same point and go in the same direction. After how many minutes will they meet again at the starting point? Here, Sonia completes one round in 18 minutes, 2 rounds in 36 minutes, 3 rounds in 54 minutes and so on. Whereas Ravi completes one round in 12 minutes, 2 rounds in 24 minutes, 3 rounds in 36 minutes and so on. Here we observe that they will meet after the common multiple of 18 and 12. So, the least common multiple of 18 and 12 is 36. It means that after 36 minutes, they will meet again at the starting point. It means that they will meet after 36 minutes, 72 minutes, 108 minutes and so on. So, in all these, the least one is 36. So, they will first meet after 36 minutes. So, the word least is used here for least common multiple. I think you all will be clear this word.